So welcome to part 3 of lecture 28. In the last part, we introduced the Cauchy-Schwarz inequality. And in this part, I just want to show you some examples about why this inequality is so great. Okay, and part of the reason is you can now start proving all sorts of kind of interesting inequalities, provided you set up your inner product at the beginning. So let me give you kind of a standard example, which is showing that if you give me any two n numbers, okay, so we'd say that the first n numbers are x1 to xn and y1 to yn are the second n numbers, and I take this product, x1 times y1 plus x2 times y2 and so on, and I square it, that's always going to be less than or equal to squaring each of the xi's and adding them together and multiplying it by squaring all the y's, adding them together and multiplying them together. Okay, so this is inequality. If we were to be asked to prove this, might at first glance be kind of an extremely hard thing to prove. However, it actually just follows out from the Cauchy-Schwarz inequality. Okay, and the trick is to find the right inner product space in inner product. Okay, and so here we're just going to let V be Rn, and we're going to use the standard Euclidean inner product. Okay, so what we're going to do is now let's take a vector x, x1 up to xn in Rn, and we'll take another vector y, y1 up to yn in Rn. Okay, so oops, clean that up there. So by Cauchy-Schwarz, what we have is that the absolute value of x and y, the inner product of x and y is less than or equal to the norm of x times the norm of y. But this is just applying Cauchy-Schwarz, but now you unpack it using the standard Euclidean inner product, right? Because what is this particular term right here? The inner product of x and y is simply x1, y1, x2, y2, up to x and yn. And on this side, what's the norm of x? Oh, sorry, maybe I need to put all squares here. So squared. And what's happening on this side? This is the norm of x squared, and that's just x1 squared up to xn squared times y1 squared up to yn squared. And there you go. If you didn't actually, the inequality now just follows from the finding the right vector space and the right inner product and applying the Cauchy-Schwarz inequality. Okay, so let me give you kind of another example, and this is kind of almost like a math contest type question, right? Which says for all positive real numbers a, b, c, and d, 16 is less than a plus b plus c plus d times 1 over a plus 1 over b plus 1 over c plus 1 over d, right? And so this, you might see it on a math contest or some homework assignment. And the real trick is you have to be able to rewrite this so you could apply the Cauchy-Schwarz. Okay, so I'll put that right here. You want to rewrite this as somehow the absolute value of the inner product being bounded by the inner product, the norm of x times the norm of y. Okay, and so the real kind of insight to these problems is picking the right space, the right inner product, and the right vectors. Okay, so it actually follows pretty easy if you set v is equal to r4 and use the standard inner product. And then the real trick is now pick the right vectors, right? So we're going to pick the vector x to be the square root of a, the square root of b, the square root of c, and the square root of d. And we're going to let y be equal to 1 over the square root of a, 1 over the square root of b, 1 over the square root of c, and 1 over the square root of d. Okay, and then the inner product of x and y is the standard dot product from first year linear algebra, right? So this gives me square root of a times 1 over the square root of a plus all the way over to square root of d divided by the square root of d gives me 4. Okay, so by exercise 1, notice that, or not exercise, but example 1, what I'm just going to do is I'm just going to apply this result right here, this inequality right here, with these particular vectors, and so I get 4 squared is less than or equal to square root of a squared up to the square root of d squared over 1 over the square root of a squared over 1 over d squared. And once you clean this up, you get rid of the square roots and the squares, you get the right-hand side, and 4 squared is 16. Okay, so this is an example of the Cauchy-Schwarz. Okay, here's an old comic, and they talk somewhere in here is a statement about Cauchy-Schwarz, which is right over here. Okay, so here it says the square of the integral is the product of two functions is less than or equal to the product of the integrals of the square of each function. Okay, so that's quite a mouthful, and it's saying that that's what the Cauchy-Schwarz inequality is. Okay, so let me kind of explain why that's true. Right? If we now take the vector space V to be all polynomials with real coefficients, we have that this is an inner product, right? The inner product of P and Q is defined to be the integral from -1 to 1 of this product. So if we take the square, you take the inner product of P and Q and then take the absolute value in the square, we're getting the integral from -1 to 1 of Px, Qx, dx squared. And Cauchy-Schwarz, right? This right here is the this inequality here is Cauchy-Schwarz, which is saying that, well, that should be less than or equal to the norm of p squared times the norm of q squared, right? So the norm, that just means the inner product of p with itself, the inner product of q with itself, and so that just is equal to -1 to 1 px squared dx. And this is -1 to 1 of qx squared dx. Okay, and that's exactly what they're saying in the comic. The square of the integral of the product of two functions, right here, the square of the integral of the product of two functions is less than or equal to the product of the integrals of the square of each function. So we're squaring each function and then taking its integrals. Okay, so that's another way of saying Cauchy-Schwarz inequality applied to polynomials. So we'll stop here for part 3, and in part 4 we'll look at some kind of classical results from geometry.